Hi guys, and welcome back to 7 Steps to a 7 in Olympiad Algebra. In the last video, we were looking at integer functional equations, and in the video before that, we introduced functional equations and some common techniques for solving them. As we saw in the last video, we often had various techniques for solving integer functional equations, and they all use the properties of the integers. For example, they use a property, that we can take steps up, so f of n plus 1 equal f of n plus 1 implies that we have something of the form like n plus c, because we just keep stepping up. But in this video, what we're going to be doing is exploring a different type of domain/codomain that has other various properties, but also has some weaknesses. And it is basically returning back to the real numbers. And to see what can go wrong with the real numbers, let's go ahead and first analyze Cauchy's functional equation again. So in the first video, we solved Cauchy's functional equation, f of x plus y equals f of x plus f of y, over the rational numbers q and the integer z. Because for the integer z, it's again just step up. And for the rational numbers, it is using the fact that every rational number is p over q. But then what if we have this equation over the real numbers? Then this becomes slightly hard because we don't know how we can exactly solve this. And as it turns out, even though we know that, like, for example, f of x is equal to cx for x in the rational numbers, because we know that the rational numbers are just a bunch of real numbers, and we can just apply the same arguments to get this. But this is not true for all real numbers. And in fact, we can have some pretty bizarre solutions to this functional equation. And it's a very, very different story over the rational numbers and the integers. Unfortunately, without real analysis or higher math, there's not exactly a way to categorize all of the solutions to this functional equation here over the real numbers. However, it is possible to categorize what their properties are. And for example, if we have a nonlinear, then it satisfies that it is continuous nowhere. It can also go all over the place on any open interval. So suppose you have like this interval 0, 1. Then the function just goes like bizarre and haywire. Like it can just do like all sorts of weird stuff. So it can have arbitrarily large and arbitrarily small values on any open interval. And then we also have that because it's not exactly continuous and it goes all over the place, it is never increasing or decreasing on any open interval. And finally, we have that whenever we plot this function f, so I'm going to go ahead and give a bigger picture here. So we can have all these points over here. It's completely random. Any circle you draw in the plane, it can be like here, for instance, will always contain a point of f, no matter how small I draw it. So if I draw like this small, you can still find something in there. So that means that any like open disk contains f of x. So the point is that these nonlinear solutions to the Cauchy functional equation over the real numbers are incredibly bizarre. And if we show that one of these properties don't hold, we just need to show one of them, then we know that f is linear. So for example, let me go ahead and erase all this. So for example, if we can go ahead and show that f of x is greater than or equal to negative 1000, for 0 is less than or equal to x is less than or equal to 0.01, then that means that f is linear. Because otherwise, if f was not linear, it would go absolutely haywire. It would have values greater than 10,000. It would have values greater than negative 10,000 or smaller than negative 10,000, so on and so forth. It just goes absolutely nuts. And oftentimes, the functions you will be working with satisfy this good property. Now, to make sure that we're working on the same page, let's go ahead and solve the Cauchy functional equation over a pretty related domain, actually, domain and codomain. So we're going to be solving this from the real numbers, the positive ones, to the positive ones again. Now, you might think that the same exact story applies over here, where we're just going to get a bunch of pathological solutions. Let's go ahead and work through it. So first, we know that f of x equals cx for our constant c for all x inside the rational numbers. So far so good. That's what we know. Now we want to see how we can fix this to go from the rational numbers, which are the positive ones here, to the real numbers, the positive ones. So we kind of have to find all the values in between. And now we can go ahead and try seeing what would a pathological solution look like. And we know that if we have a pathological solution, it would be continuous nowhere. And that we can't really seem to do stuff with that since we don't know if it is continuous or how to prove it is continuous. And we also know that it goes haywire, meaning that it has arbitrarily large or small values. But it doesn't seem like we can obtain a good bound on f without some work. And actually, we can technically say like f of x is greater than 0 for all x greater than 0, which would also solve the equation. But let's go ahead and see a different approach from this, because there's a much simpler solution rather than appealing to this haywire fact. And then we have it is never increasing. So let's try working with never increasing or decreasing. So if f was increasing, how could we prove this? Well, we want to prove that like if x is less than y, then f of x is less than f of y, or something like this. And we want to somehow use the fact that f of x and f of y are greater than 0. So we want to somehow do something like that. And from this, we can just try the simplest bound possible. And it is that because this is greater than 0, we know that this is greater than f of x. So therefore, f of x is less than f of x plus y. But then we know that x is less than x plus y, and these can just be about anything otherwise. For example, if we want to prove that like f of 0.1 is less than f of square root 2, for instance, we can go ahead and set x equals 0.1, y equals square root 2 minus 0.1. And then we would have this. So therefore, we have proved that f is increasing, which means by our theorem that we said earlier, it should be the linear solution. But how exactly does increasing imply linear? Well, suppose we have a real number like the square root of 2. We want to prove that f of 2 is c times the square root of 2. Well, here's a trick with real numbers, or irrational ones. We can keep surrounding the square root 2 into intervals. So for example, square root 2 would be less than 17 over 12, but also greater than 41 over 29. And therefore, we know that f of this is less than f of this is less than f of this. And these guys are rational numbers, so 41c over 29 is less than f of square root 2 is less than 17c over 12. And we just keep getting tighter and tighter around this one here. and eventually we single out on this value here. So therefore, the fact that f is increasing ends up proving that f is linear as well. And this is a type of solution you would find when you want to try bounding something, or trying to use something about f being very tame. Because oftentimes you're going to find that f being tame will end up solving the functional equation. You just have to figure out how it is tame. Now, so far, as we see, when we have something like a Cauchy equation, or we can only ever find the value of f of x when x is in the rational numbers, we often have to either use some sort of bounding condition or show that it is tame in some way, like it is increasing or continuous, or just try something else entirely. And right now we're going to be taking a look at some common ways to bound things. And in order to simplify our analysis, what we're going to be doing is work over the positive real numbers, because that way it will be easier to explain some of these bounding techniques. And often the philosophy of bounding is to just come up with the dumbest things possible. For example, f of x greater than 0, and that can often create some of the stronger bounds you'll see. And we're going to go ahead and look at an example here to see how bounds can solve a problem. So we have this problem from the 2005 IMO shortlist, and it is as follows. Find all functions f from the positive real numbers to itself, satisfying f of x f of y equals 2f of x plus y f of x. Now, our first objective is to find all the linear solutions. And you can go ahead and do that on your own. But from what it seems, the only linear solution that satisfies positive real numbers to itself is f of x equals 2. And that's the only linear solution. Now, this is super suspicious, because what if there's another linear solution? And you could go ahead and check the quadratic case and make sure that there are none there. So there could be a super weird solution besides this obvious one. But for now, we're going to go ahead and assume that it's the only one. So f of x equals 2. Now we want to see how we can solve this functional equation. And as we saw in the first functional equations video, we really like this idea where we can cancel things out with one another. So for example, we can cancel this one here with this one here and get f of y equals 2. And we get something independent of x in a way. But we can't exactly cancel these unless we know some more information. Like if f of x equals f of x plus y f of x, then the only way we can exactly ensure this without additional information is if x equals x plus y f of x, or equivalently that y f of x is 0. But this can't happen over the positive real numbers, so we have to alter our approach. Now, this should highlight the first benefit of the positive real numbers, and it is that numbers are greater than 0. And that can give us some super cool bounds. Now, we can go ahead and try making this f of y here equal to that one here. So f of y equals f of x plus y f of x. Now, the only way we can ensure this again is if y equals x plus y f of x. We could try solving for x, but we have this f of x here intertwined. So we can try solving for y instead. We get like y 1 minus f of x is equal to x. And thus y equals x over 1 minus f of x. And so if we plug in this y, we should see everything cancel in front of our eyes. And when we do that, we end up getting f of x equals 2, and we are done. Or are we? Because when can we exactly plug this value of y in? Well, because we're working over the positive real numbers, it must be greater than 0. And that means that f of x must be less than 1. But if f of x is less than 1, that means that f of x is equal to 2 by just plugging this y in. And that makes it impossible because 2 is not less than 1. So the only way that we can have something work out in the end is if this value here is always less than 0. Or in other words, that f of x is always greater than or equal to 1. So let me go ahead and write that up. So f of x is greater than or equal to 1 for all x. All right, that's cool because now we have a pretty nice bound on f. And note how we use the fact that we're working over the positive real numbers to our advantage. And let's see if we can keep going. And we want to try making an advantage of this bound we have here. So we can try using it on one of these two sides here. So for one, we could say that it is greater than or equal to f of y, or greater than or equal to 1. And that would mean that f of x plus y f of x is greater than or equal to 1/2. But we kind of already know this from that. So it seems like bounding the f of x, f of y side won't do anything. So what if we instead bound on this side? Then we end up getting that it is greater than or equal to 2. And thus we get f of x, f of y is greater than or equal to 2 for all x and y. And now we have some really useful information because the product of any two values of f is at least 2. And this seems super strong because if we plug in x equals y, for instance, we end up getting f of x squared is greater than or equal to 2, or f of x is greater than or equal to the square root of 2. And note how by just using this bound here, we got a stronger one. F of x is greater than or equal to the square root of 2. And we can try to keep going in this manner. So we have f of x, f of y is greater than or equal to 2 square root 2, and f of x is greater than or equal to 2 to the, I think this would be 2 to the 3/4. And then we can keep going, and f of x squared is greater than or equal to 2 times 2 to the 3/4. F of x is greater than or equal to 2 to the 7/8. And we just keep increasing this exponent over and over and over again. And we can prove by induction that f of x is greater than or equal to 2 to the 1 minus 1 over 2 to the n. And this general statement is true. And we can just keep increasing n all the time. And by keep increasing this, we know that any value of f less than 2 won't exactly do. And thus, we have proved by using these bounds that f of x is greater than or equal to 2 for all x. Now, the thing that we want to note here is that we did all of this by just using bounding. We just used the dumbest bounds we could come up with and use them to prove a pretty powerful result. And this seems super powerful, and we can't exactly improve it since we know that f of x equals 2 is a solution. Anyhow, let's go ahead and see what else we can do. And let's return to our original equation equipped with this. And we can try some more common techniques. So because there is asymmetry on this right-hand side, we can try exploiting it, because that's something you do whenever you have something asymmetric on one side and symmetric on the other, as we saw in an example in the third video. So this means that f of x plus y f of x is equal to f of y plus x f of y. Now, if we're expecting f of x equals 2 to be the only solution, then we know that we don't get anything particularly useful, because obviously these two are equal. But what if it was like an ordinary linear equation, where if we have that it goes upward and it never repeats the same value? In other words, it's injective. If f of k equals f of L, then k equals L. Then this would mean fx plus y f of x is equal to y plus x f of y for all x and y. And then if we solve for y, or f of y, we get f of y is equal to x plus y f of x minus y over x. And we can go ahead and plug in x equals 1 if we want to get y f of 1 minus y plus 1. And this ends up giving us a linear solution. But we check that all the linear solutions must satisfy f of x equals 2. So we know that this won't exactly work. And therefore we have to have that we don't have an increasing linear solution like this. In other words, we have two values of f are equal. And suppose that we have f of r is equal to f of s here, where r and s are distinct real numbers. Then what we know is that one of x and y here have to be r or s, because then we can go ahead and work with that. So suppose that, for example, x equals r. Then we want x plus y f of x here to be equal to s, because then we can get the cancellation that we wanted in the beginning. Because remember, we wanted to make these two equal, but couldn't do that since we didn't know any other information about f. Well, now we know information about f, so we can make these equal. So r plus y f of r equals s, so y equals s minus r over f of r. But then we have to face the exact same issue that we did when trying to prove that f of x equals 2 to begin with. And that was that we can't plug in negative inputs. So this has to be greater than 0 or s greater than r. And this means that we hit an issue. If s is less than r, then this can't work out. But we only chose x equals r. But what if x equals s? Then we could get r greater than s. And that could end up working out. So we can just swap the order of r and s and get it to work out. And thus we can assume that, for example, r is less than s, making this greater than 0. And that means that if you plug in this value of y here with x equals r, we get that these two cancel out. And what is left is f of y equals 2. And thus we have found an exact value of y for which f of y is 2. And this basically means that this is the strongest bound we can get. And we're going to go ahead and write this as y equals s minus r over f of r is equal to a for simplicity. And thus we know that from this discussion, we have f of a is equal to 2. So f of a equals 2. Okay. So the special thing about a is now we know an exact value of an output of f. And because we know an exact output of f, magic can happen. So for example, let's go ahead and set a equals x now. Then what we end up getting is f of y, 2f of y, is equal to 2f of a plus 2y. And this means f of y is equal to f of a plus 2y. And from this, we know that if we plug in a value here that makes one of these a, we can get the other one to be a value of a for which f of a is 2. So if this is a, that means 2y is 0, which is bad. So what if y equals a? Then f of a is f of 3a. But then f of 3a here, because it's f of a, is also 2. And thus f of 3a is equal to 2. So in essence, if f of something is 2, we can triple it to get another value, which it gets 2. And by this logic, we can repeat it to get f of 9a equals 2, f of 27a equals 2, and so on and so forth. We just keep tripling the value here. All right, so now we have a bunch of values for which we get f of a is equal to 2, and we want to somehow return back to our problem. And we want to see what exactly we haven't used. And the thing we haven't used yet is this bound we have here. F of x is greater than or equal to 2. Because if we can't incorporate this bound, then we can't really do anything. So we want to somehow use these values of a to kind of enforce the bound in a way. So we can try using the bound on this left-hand side here and get 2f of x plus y f of x is equal to f of x f of y is greater than or equal to 2 times 2, which is 4. And so f of x plus y f of x is greater than or equal to 2. Well, what if it was equal to 2? Then from here, we end up getting that this one here must be one of these values here. So suppose that we have f of b equals 2, and x plus y f of x is equal to b. That would mean that y equals b minus x over f of x. And if we plug in this y, we end up getting that this here is actually equal to 4. And which means that because we have our bounds here, and we used f of x, f of y is greater than or equal to 2 times 2 is greater than or equal to 4, and this is also 4, equality must hold everywhere. Because otherwise we're going to get a small change and that will break the inequality. So therefore this means that f of x is equal to 2. And that solves the problem. Or does it? Because you might have noticed again that this has to be greater than 0, or x is less than b. So the only thing this proves is that f of x is equal to 2 for all x less than b. So we have it's less than 2 for x less than a, x less than 3a, x less than 9a, so on and so forth. And we can just keep increasing this to get that any value of x is less than something here, and we just use that value of b. And when we use that value of b, this y is well defined, and the inequalities must have equality everywhere. And thus f of x equals 2 is the only such solution to this functional equation. The reason why I like this problem a lot is because almost the entire solution relies on bounding. And it goes to show how bounds can take you very, very far. Granted, a lot of this problem wasn't just bounding, and it was just a lot of careful manipulations, but I wanted to discuss it because the main observation that f of x is greater than or equal to 2 didn't exactly use any super special inputs. We just started from f of x is greater than or equal to 1 and built an inductive bound in a way. And that gave us our main bound that we used in the solution. So let's go ahead and take a look at our end of video example, which I think is a really good one because it highlights a lot of the principles we've been looking at in this video. And it goes as follows. Let R plus denote the set of positive real numbers. Find all functions f from the positive real numbers to itself, such that for each x in the positive real numbers, there is exactly one y in the positive real numbers, satisfying x f of y plus y f of x is less than or equal to 2. So go ahead and try out this problem on your own, and we'll go ahead and pause the video right now. And when you're ready to discuss it with me, hit the play button. So hopefully you've had the chance to work on the problem now. So let's go ahead and discuss it together. The first order of action with any functional equation is to try finding all the solutions we can. And unfortunately for us, if we try out the linear solutions, for example, we end up getting something like x, y plus y, x is less than or equal to 2, or x, y is less than or equal to 1. And there isn't exactly one positive real number satisfying this, because there are infinitely many. So we're going to end up with this kind of issue when f is not linear. And something similar happens if f is quadratic or any other like higher degree. So we're already starting off with no solutions. So this doesn't seem particularly good. So what exactly can we do now? Well, let's go ahead and try plugging some basic things in. So we know that if we plug in x, we can try getting 2x f of x is either less than or equal to 2 or greater than 2. Now, we know that for every single x, there is exactly one y. So it's like these x and y are paired up together. So I'm going to go ahead and call these x and y that are paired up together buddies. And if x is not buddies with itself, that means that 2x f of x is greater than 2, or f of x is greater than 1 over x. And then we can try using this bound to our advantage in the most stupid way possible. And then we end up getting something like x over y plus y over x. Because we know that this should be less than or equal to 2, and we just use that bound here. But then this thing should look really suspicious, because this seems like an inequality that should not be true. Specifically, if we multiply both sides by xy, we get x squared plus y squared is less than or equal to 2xy, which is just false by AMGM, unless x equals y. So the only way we can have that this inequality here is true, given this here, is if x is equal to y, and that's not always true. So therefore, we've gotten a contradiction, and it seems like x has to be buddies with itself. So x buddies with itself. And this means 2x f of x is less than or equal to 2, so f of x is less than or equal to 1 over x. And for all other y, we end up getting x f of y plus y f of x is greater than 2. Okay, so if y is not equal to x, then it makes this one here greater than 2, and this one here makes it less than or equal to 2, there's got to be some sort of tipping point. We can't have this like 1.95, and then this just suddenly goes to 2.01. That doesn't exactly make sense. So the thing that makes the most sense here is if this were exactly equal to 2. So 2x f of x equals 2, and f of x equals 1 over x. And if we end up checking this function, we get that it works. Because whenever x equals y, we get that it's 1 plus 1 equals 2 is less than or equal to 2. If they're not equal, we get x over y plus y over x is greater than 2 by AMGM. And thus, f of x equals 1 over x actually fits. So this is very, very good to know. So we want to somehow use this bound here to our advantage, given this thing here. and also the solution set here. So suppose that we have something like f of a is equal to b. What if b was not equal to 1 over a? So b is not 1 over a. Then because of this bound over here, we discovered that this must be less than 1 over a. And we want to somehow do something with this over here. So because we know the value of f of a now, it's b, we can try plugging in x equals a, provided that y is not equal to a. Then when we do this, we get a f of y plus yb is greater than 2. And now we want to somehow turn this into a more useful bound. And we can again try using the dumbest bounds we know, that f of x is greater than or equal to 1 over x. And when we do this, we end up getting something like a over y plus y over b, or yb. Now, we want to somehow get these two squeezed together in order to force this to be some value. So for example, what if we have f of 1 is equal to like 0.9? Then we have 0. Or this should be 1 over y plus 0.9y is greater than or equal to, this should be 1 f of y plus 0.9y. And this is greater than 2. And this should imply that this here is greater than 2 always. But when exactly is this expression here minimized? Well, this expression here is minimized by AMGM when it is equal to 2 squared 0.9. And that's less than 2. And therefore, if it achieves this minimum when it's less than 2, this is just guaranteed to fail. So therefore, this inequality idea, where we just use the dumbest bound possible and use AMGM, seems to be the key idea. So that means that we know the minimum here is 2 root AB, and this must be greater than 2. And we're assuming that the place where the minimum occurs, which actually turns out to be square root A over B, is not equal to A. So if this happens, then 2 root AB is greater than 2, or AB is greater than 1. But then we have this information here, which implies AB is less than 1. But AB cannot be less than 1 and greater than 1 at the same time. So by using these dumb bounds, we ended up getting that these two must be equal, and thus A equals 1 over B. And this ends up proving that f of A is 1 over A, and hence that f of x equals 1 over x for all x. Now, the main idea of this problem that I want you to take away is that it is always okay to use the dumbest bounds possible, because often that's all you get to work with. And by repeatedly using these dumb bounds, we can get something very powerful. And for the level of problems that you'll be working with in easy Olympiad algebra, these bounds often don't need to be very strong. They can just be as simple as like f of x is greater than 0, f of x is less than or equal to 1 over x from some easy observation, or something like that. When you'll get to higher functional equations or harder ones, you're going to see more concrete and more sophisticated bounds, ones that require lots of thinking and motivation to come up with. And they're often very, very weird. But we're not going to worry about those now. But for now, you just need to know that these bounds can be very, very simple or stupid. So thank you so much for watching this video. Please subscribe if you'd like to see more, and I'll see you guys in the next video.